In this lecture, we will explore the narrowband angle modulation and its similarities with the amplitude modulation. Narrowband angle modulation shares several characteristics with amplitude modulation, but before doing anything, let's have a quick look at the formulas of the both modulation. For amplitude modulation, amplitude modulated signal St is equal to AC into 1 plus K into cos omega mt into cos omega ct, and for angle modulation, St is equal to AC into cos 2 pi fct plus Kp into mt for phase modulation, and St is equal to AC into cos 2 pi fct plus 2 pi kf into integration from 0 to t m tau d tau for frequency modulation. This 2 pi fc can be written as omega c. Now, both the forms of angle modulation can be simplified into a generic form as St is equal to AC into cos theta it. Here, theta it is the instantaneous angle of the angle modulation, and this instantaneous angle theta it can be represented as theta it is equal to 2 pi fct plus phi t, which can be written as omega c t plus phi t. Here phi t represents the change in the angle of angle modulated signal from its unmodulated value or instantaneous deviation. Now we can express this angle modulated signal as St is equal to AC into cos omega ct plus phi t using the trigonometric identity for cos a plus b, which is equal to cos a cos b minus sin a sin b. We can expand this angle modulated signal St as St is equal to AC into cos omega ct into cos phi t minus sin omega ct into sin phi t. By comparison, for phase modulation, this phi t is equal to Kp into mt, or if we put the value of message signal mt as am cos 2 pi fmt, this phi t will become Kp into am cos 2 pi fmt. And for frequency modulation, this phi t is equal to 2 pi kf integration from 0 to t m tau d tau. Again, we can put the value of message signal m tau, then this phi t will become kf into am divided by fm sin 2 pi fmt. In the narrowband modulation, we approximate this phi t is very small and falls between the 0 and 0.2. This allows us to approximate cos phi t is equal to 1 and sin phi t is equal to phi t. With these approximation, we can simplify the angle modulated signal St as St is equal to AC into cos omega ct minus sin omega ct into phi t. Now let us understand effect of this angle modulation from the singleton modulation. Consider a singleton modulated signal mt is equal to am cos 2 pi fmt, and for the phase modulation, the instantaneous phase deviation phi t can be given by Kp into mt. Now we will substitute this value of phi t in the equation of narrowband angle modulation, and then St can be written as St is equal to AC into cos omega ct minus sin omega ct or sin 2 pi fct and Kp into mt. Now we will put the value of mt as am into cos 2 pi fmt. Now we will divide and multiply this term by 2. Now we can use the trigonometric identity of 2 sin a cos b, which is equal to sin a minus b plus sin a plus b. By applying this trigonometric identity, this term will become Kp into am divided by 2 sin 2 pi fc minus fm into t plus sin 2 pi fc plus fm into t. Now we will multiply AC with both the terms. Then this amplitude modulated signal will become AC into cos omega ct minus AC into Kp into am divided by 2 sin 2 pi fc minus fm into t plus sin 2 pi fc plus fm into t. This above equation shows that narrowband phase modulated signal has three components. First one is the carrier component, which is equal to AC cos omega ct. Second one is the lower sideband component, which is represented by AC divided by 2 Kp into am sin 2 pi fc minus fm into t, and the third one is the upper sideband component, which is equal to AC by 2 Kp into am sin 2 pi fc plus fm into t. The bandwidth of this narrowband phase modulated signal is the difference between maximum frequency fc plus fm and the minimum frequency fc minus fm, which will result in 2 FM. So just like the amplitude modulation, narrowband phase modulated signal also has a bandwidth of 2 FM. Although the bandwidth of this narrowband phase modulated signal is 2 FM, just like the amplitude modulation, but a key difference between these two modulation is that the sidebands are shifted by 90 degrees relative to the carrier. Let's understand this phenomena from the equation of the narrowband phase modulated signal. Now the narrowband phase modulated signal can be written as AC into cos omega ct minus AC by 2 Kp into am cos minus cos pi by 2 plus 2 pi fc minus fm into t minus cos pi by 2 minus 2 pi fc plus fm into t. And now we can take this minus outside the square bracket, then it will become St is equal to AC into cos omega ct plus AC by 2 Kp into am cos pi by 2 2 pi fc minus fm into t plus pi by 2 2 pi fc plus fm into t. Now this pi by 2 fc can be written as omega c, and this pi by 2 fm can be written as omega m. Then narrowband phase modulated signal will become St is equal to AC cos omega ct plus AC by 2 Kp into am cos pi by 2 omega c minus omega m into t plus cos pi by 2 omega c plus omega m into t. There is also a dissimilarity as the two side frequency components are shifted in phase by 90 degrees relative to the carrier component, and the phasor diagram also confirms this. For the phasor diagram of the narrowband phase modulated signal, the carrier signal, which is AC cos omega ct, is represented by a horizontal phasor with the amplitude AC. Next, we draw a line that is 90 degree phase shifted with respect to this phasor, or this line can be represented by AC into cos pi by 2 plus omega c into t. Now we will move this line plus omega m to generate another phasor AC cos pi by 2 plus omega c plus omega m into t. And we will also move this line by an angle of minus omega m to generate another phasor AC cos pi by 2 plus omega c minus omega m into t. The amplitude of the phasor AC cos pi by 2 omega c plus omega m into t will be replaced by kp into am into AC divided by 2, and this phasor will become kp into am into AC divided by 2 cos pi by 2 omega c plus omega m into t, representing the upper sideband. Similarly, we can replace the amplitude of this vector by kp into am into AC divided by 2, which will represent the lower sideband, and this vector will become kp into am into AC divided by 2 cos pi by 2 plus omega c minus omega m into t, and this will represent a lower sideband having the amplitude kp into am into AC divided by 2. Narrowband frequency modulation. So according to the narrowband approximation of the angle modulated signal, the narrowband angle modulated signal st is equal to AC into cos omega ct minus sin omega ct into phi t. Phi t for the frequency modulated signal is kp into am sin omega mt, as we have previously calculated. Now we can put this value in the approximation of narrowband angle modulated signal. Then it will become, now we can put the value of phi t as kf into am divided by fm sin omega mt in the approximation of narrowband angle modulated signal, and then narrowband frequency modulated signal will become st is equal to cos omega ct minus sin omega ct kf into am divided by fm sin omega mt. Now we will divide and multiply this term by 2. Then we will employ the trigonometric identity of 2 sin s sin b, which is cos a minus b minus cos a plus b. Here this angle modulated signal st will become AC into cos omega ct kf into am divided by 2 fm cos omega c minus omega m into t minus cos omega c plus omega m into t. Now we will multiply AC with the terms. Then angle modulated signal will become st is equal to AC into cos omega ct AC by 2 kf into am divided by fm cos omega c plus omega m into t minus omega c plus omega m into t. Here the narrowband frequency modulated signal has a carrier component of AC into cos omega c t, which oscillates at the carrier frequency fc, and the upper sideband of AC by 2 kf into am divided by fm cos omega c plus omega m into t, and which oscillates at the frequency fc plus fm, and a lower sideband of minus AC by 2 kf into am divided by fm sin omega c minus omega m into t, which oscillates at the frequency fc minus fm. These components are similar to amplitude modulated signal, but the key difference is in the relative amplitudes of the sidebands and their phase relationship. Hence, the components of the narrowband frequency modulated signal may be represented by the following phasor diagram. In the phasor diagram, the carrier phasor AC cos omega ct is represented by a vector aligned along the real axis or horizontal axis. The upper sideband or USB and the lower sideband or LSB phasors positioned such that they lead the carrier phasor by an angle of omega m respectively. Both the sideband phasor have an amplitude of AC by 2 kf into am divided by fm. And since there is a minus sign before the lower sideband, we can redraw this phasor, and this will look like this. A minus sign in this cosine term represents a phase shift of 180 degree in the corresponding phasor. The phasors of USB and LSB are symmetrical but in opposite direction. Hence, USB phasor rotates counterclockwise and LSB phasor rotates clockwise. Again, the bandwidth of the narrowband frequency modulated signal is the difference between maximum frequency fc plus fm and the minimum frequency fc minus fm, which will give us 2 fm. Let's compare the phasor diagram of the narrowband phase modulated signal with the singleton amplitude modulated signal. The singleton amplitude modulated signal can be written as AC into 1 plus k into cos omega mt into cos omega ct. Now we will multiply cos omega ct with both the terms. Then we will divide and multiply the term k into cos omega mt into cos omega ct by 2. Then we will employ the trigonometric identity of 2 cos a cos b. Then this term can be written as k by 2 cos omega c minus omega m into t plus cos omega c plus omega m into t. Now this is the phasor diagram for singleton amplitude modulated signal. Let's see the phasor diagram for this a single tone amplitude modulated signal. In the phasor diagram, the carrier phasor AC cos omega ct is represented by a vector aligned along the real axis or horizontal axis. The upper sideband and the lower sideband are positioned such that they lead and lag the carrier phasor by an angle of omega m respectively. Since both sideband have an amplitude of and both sideband phasors have an amplitude of m into AC divided by 2. And if we compare this phasor diagram with the phasor diagram of narrowband phase modulated signal, then we can see that the phasor diagram for the phase modulated signal is different from amplitude modulated signal. And in the amplitude modulated signal, the resultant phasor representing the amplitude modulated signal has a different amplitude from that of the carrier phasor, but always in phase in it. Although both the narrowband frequency modulated signal and the amplitude modulated signal have three sinusoidal components, but their phasor diagrams clearly show that the main difference is that amplitude modulated signal affects the amplitude of the carrier while frequency modulated signal affects its phase. The difference is due to the distinct method used to generate the two different types of modulation. Now let's see the spectrum for the narrowband frequency modulated signal. Based on this equation, we can represent this narrowband frequency modulated signal as a two-sided spectrum illustrated here in this figure. The spectrum includes a carrier at the frequency Fc and the two sidebands located at Fc plus Fm and Fc minus Fm corresponding to the modulating frequency Fm. Now let us see the generation of this narrowband angle modulated signal. For the generation of narrowband angle modulated signal, let us again write the narrowband approximation of angle modulation, which is St is equal to AC into cos omega ct minus sin omega ct into theta into phi t. This phi t is equal to kp into mt for phase modulation, and this phi t is equal to 2 pi kf 0 to t m tau d tau for frequency modulation. For the generation of this narrowband angle modulation, at first the input signal mt is integrated and it becomes m tau, the integration of from 0 to t m tau d tau, then it is amplified with the 2 pi kf, where kf is the frequency modulation constant, and this step produces the frequency modulation component denoted as phi t. Now the same input signal mt is also amplified with a gain of kp, where the kp is the phase modulation constant, and this amplification results in the phase modulation component. A carrier signal AC cos omega ct is generated, where AC is the carrier amplitude and omega c is the angular frequency. This carrier splits into two orthogonal components, AC cos omega ct, which is the in phase component, and AC sin omega ct, which is the quadrature component, achieved by 90-degree phase shift. Now the frequency modulation component phi t modulates with the quadrature component AC sin omega ct, and the phase modulation component modulates with the in phase carrier component or AC cos omega ct. Now the modulated in phase and quadrature components are summed together to produce the narrowband angle modulated signal St, which has the both frequency and phase modulation effects. The resulting the narrowband phase modulated signal St is equal to AC cos omega ct plus AC phi t sin omega ct. This process is foundational for generating the narrowband phase modulated signal and is often used in the application like Armstrong method for wideband frequency modulated signal generation. This concludes our discussion for this lecture. In the event that you have any question regarding this presentation, feel free to post them in the comment section, and don't forget to hit the subscribe button. See you in the next one.